Okay, so now that we have the NDK installed on our file system, the next step is for us to actually build something with the NDK, and then through that, hopefully understand how to use it and what it has or doesn't have. So what I'm going to do is actually build an application in the Eclipse environment, and then later on compile it from the command line. In order to build this, you will need the latest version of Eclipse, the latest version of the SDK, at least one platform, the latest version of the ADT, which is a tool set or plugin for Eclipse, already pre-configured and pre-set up. If you don't know how to do this, I suggest taking a look at d.android.com and then clicking on the SDK tab. Now, this is what we'll end up seeing. Let me actually, before we get started, switch over to my browser and switch over, actually, not to my browser, but this preview. Essentially, this is what we'll do. We'll create a Java library in which we will define some native methods. So those methods, as you will see, will implement later on inside of a C source file. Now, before we get there, what we'll do is, of course, we'll compile this library using Java-C, or Eclipse will compile it for us into the actual class itself. And then we'll use a tool called Java H-JNI to extract a header file from the original Java library, or better yet, the class file, which will then implement in our C++ source file. After we implement this, we'll actually create a makefile. There's two different parts to the make build system, the Android.mk and the application.mk. You'll see that only this one is required. We'll then run the Ndk build. This is essentially the step where we'll do the Ndk build, which is why we install the Ndk. We'll produce the dynamic library. We'll then write a little bit of, some sort of a client app that will be, of course, compiled again by Eclipse into a class file. And then this application will use or attempt to use the Java library or the Java class, which in turn will load the native library and essentially provide the implementation that this application or this client application expects. Okay, that's our goal. Now, to get started, what I'm going to do is I'm going to go and create a new Android project. I'm going to give it some sort of a name, like for example, in this case, I'm just going to use Fibonacci as an example application. So I'm going to call this Fibonacci, say native. And I'm going to click on next, choose a build target. In this case, I have quite a few. I could choose any of the build targets. We're not going to do anything special, at least nothing that wouldn't work on, say, API level 8 or 9, but doesn't matter. In this case, I'm choosing the latest one. Clicking on next, and then I'm going to choose a package name. Like, for example, com.maracana.android.fibonacci native. Okay. And then I'm going to create an activity, for example, say Fibonacci activity. Minimum SDK 15. Again, I'm just using this as an example. Feel free to go and lower the SDK to something like 8 if you want to be able to try to run it or upload it to market, for example. So click on finish, and this builds a basic structure of my application. It's going to take a little bit of time for Eclipse to go and figure out that there is in fact the R file, and for this red section to go away. And now it's done. Okay, so the next step is for us to actually create the library itself. So we do this by right-clicking on this, the package, and creating a Java file, I should say a Java class, that I'm going to call, for example, fiblib, just some name that I chose to do, and clicking on finish. This will essentially create an simple class file. Now, this class file is just to show you this class file. It's basically this library right here. Now, you don't see this, but it's already been compiled by Eclipse into a native class. So we actually have all of this already done. Of course, we haven't defined anything there, so it's really useless at the moment. Okay, so let's go and define something. Okay, so what we'll do is define, for example, 4 different implementations of the Fibonacci, essentially, algorithm or sequence. 2 implementations are going to be written in Java, 2 are going to be written natively, and we're just going to use it to test performance. Later on, we'll introduce other things into the mix, but this is just going to be to get us started. So, for example, the naive Java implementation may look like this: public, static, long, fib, JR. I'm going to say J is for Java, R is for recursive. So given some sort of an N, which is going to also be a long, I'm going to say, well, return if N is greater or less than 0, for example, return 0. Otherwise, if N is equal to 1, return 1. Otherwise, return fib of JR of N minus 1 plus fib of JR of N minus 2. So this is how essentially the Fibonacci sequence is defined. Nothing too special, nothing too exciting. Now that I have this, I'm also going to define a native version of this method. Public static, I should say native static fib J, NR for native, long N. This is essentially J and I. What this means, I'm forgetting one part, which is the return value. I'm essentially saying here that the body of this method doesn't exist, it'll be provided natively. It's kind of like if you're creating an abstract method, this would have been an abstract class. You could say an abstract method, somebody else will implement it. Well, in this case, somebody else will be our native code, which we have to write. So then I'm going to define a version of the same Fibonacci algorithm, but this time around I'm going to use the iterative approach. So public, static, long, fib, ji, I for iterative, long n, and I'm going to say return, not quite. So for example, long previous equals, doesn't matter, -1, long result equals 1, and then for some sort of long I equals 0, I less than n, I plus plus, we are going to say give us a sum, so sum of result plus previous. Okay, so this actually matters, so that's why we initialize the previous and the result to -1 and 1, so that initially they're going to cancel out. And then previous equals result, and result equals to sum. And all we need to do is return the result. And now we have the iterative version of the Fibonacci algorithm. And finally, we're just going to go and say, for fun, public native, doesn't actually matter in which order you define them, but I like to do it this way: static, long, fib, ni, long, n. Done. So this is essentially our entire fiblib library. That's, if you take a look at this is what we've now built. So now this part is actually done. And to show you that we have even the library class, I'm going to go and open up my terminal. I'm going to go to the directory where this is located. So in this case is under, I should say, workspace, courseware, Android, out, workspace. Again, I know it's confusing. And there you'll see that I have my Fibonacci native project, and there you'll see I have the bin directory, or ls bin, classes, and then of course I can go and type com, boom, 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 and here is my class file. So that part is done. The next step is for me to build the or extract, I should say, the shared, let's take a look at this, the header file. Right now, I'm going to use a tool called java-h-jni to extract this. Later on, you'll see that you don't even need to do this step. There's another way of registering or binding native code to Java code without the need to worry about specific namespacing or the mapping rules. So for the time being, we'll actually do it this old-fashioned way. So what does that mean? First of all, I'm going to create a directory called JNI. Now, why am I creating this directory? Is because that's where NDK expects to find native code. Okay, it's by convention. And now that I have this, I'm going to run this tool called Java age-jni, and I'm going to say I want to go and class path load classes from my bin/classes directory and output the header file into, so the destination is the JNI directory. And I'm specifically looking for a class by the following name, com.maracana.android.fibonacci-native.fiblib. Enter. If everything worked correctly, under the JNI folder, I should now have this header file. So what do I do then? Well, let's take a look at it. I'm going to go into, first of all, Eclipse and do a refresh of my project, because by doing that, I get the Eclipse to discover the new folder. And now you'll see that I have this file. Let's open up this file. Notice, by the way, this file looks kind of good, meaning it's syntax highlighted. And the reason why this works is because in my Eclipse, I actually have CDT, which is a set of plugins that enable me to write native code right in Eclipse. It's not just a Java editor, it's also a C++ editor. You can certainly go and add that support to Eclipse through help and then install new software, and then you can search for CDT. Now, let's take a look at this resulting file. Why this file, what does this file define? Well, fiblib, you'll notice, has a certain package name, and it has a class name with certain native functions, or I should say methods, but ultimately they'll become functions. So now check this out. In C, we don't have the concept of of namespaces. So instead, in order for later on Java to be able to invoke these functions written in the C language, or I should say, I guess in the C language, we'll need to somehow map from the Java namespace into a flat namespace of C. And the way this is done, at least with JNI, is that this function, like for example, fibnr, is prefixed with a Java underscore the package name underscore the class name, and then finally the function name. Notice that function name takes in 3 arguments: a pointer to the environment, the point to the reference to the class within which it is to be found, and the JLong, which is essentially, as you will see, the n itself. This is the version of this function at least for this fibnr, and here's the same function for fibni. Okay. So now that we have this, the next step is for us to go and I'm going to actually copy these 2 functions like so, or I should say, it's probably easier to do it this way. I'm going to copy this entire header file like so, so copy, and then go over here and type paste. I'm actually making a copy of the entire header file. Doesn't seem like the most logical thing to do, but you'll see in a moment. So I now have a file by the same name, except that it's the .c. So just to show you what we're doing, we've now essentially done all of this. This is what we have. I'm now going and creating this file. Okay, that file, as you will see, will import from the header file, or I should say the include. So now that I have the C file, here it is, I'm going to go and have the C file include the header file. So com.maracana underscore android underscore Fibonacci native underscore fiblib.age. Okay, done. And now I'm going to get rid of this, get rid of this, get rid of this. So all I'm left with are the same function signatures or prototypes that I've done before, except that now I'm actually going to provide the bodies of these 2 functions. So here is, our first function, the fibnr, that takes in a pointer to the environment, a reference to the class, and then the n. Now, the pointer to the environment is going to come in handy later. You will see exactly how. The class is given to us so that we can reference this fiblib class. Had this been a non-static method, then we would not have been given a reference to a class, we'd be given a reference to the object. So this would have been called the J object, or it would have been of type J object. And finally, this is the n itself. So just to show you back here, remember how this fib_nr takes an n? Well, here we get that n. Now, why is this n J long? Okay, well, the thing about JNI, as you will see, is that JNI is generally meant to mostly not implement a lot of logic, but rather map Java data types onto C data types so that we can invoke code that is written just natively without any regard to Java or the JNI. So essentially what that means is that we have to map from one data type space into another. In Java and Dalvik, as a result, the data types are fixed. We know exactly what they are regardless of the underlying infrastructure or architecture. So we know that Boolean is essentially unsigned, happens to be unsigned 8 bits. A byte is always signed 8 bits. That char is unsigned 16 bits. Short is always 16 bits. Int is always 32 bits. Long is always 64 bits. Unfortunately, in C or C++, something like, for example, long will depend on the our underlying architecture. So if you're on a 64-bit platform, long is going to be 64 bits. If you're on a 32-bit platform, long is going to be 32 bits. In Java, that doesn't work that way. It's always 64 bits. So because of that, we can't really use C types without worrying that we may actually, for example, overflow our values or truncate our values. So basically, instead, we're going to use JLong. So we know exactly what the type this is. And this is really nothing more than a little type def. Where does this come from? Well, notice how here we're including this header file. Well, that header file is in turn including the jni.h. jni.h, as you will see, defines a number of things, including this JNI environment, the J class, as well as all these other data types that we now see. So let's go down here. I'm going to do the same thing that I've done, name these parameters here. I'm going to do the same thing over here. And so now it's just a matter of me implementing the code. So for example, for this version, I could just be lazy and copy the Java version. So I'm just going to, boom, copy this code. In fact, copy all of this. Go to the C implementation and literally paste it. The only difference is that now this becomes a JLong. This becomes a JLong. This over here becomes a JLong I. So I can't, this is not quite C99, so I can't declare this inside of the for loop statement. This becomes a JLong. Okay. This becomes a, basically, same as before. Nothing too exciting. Move this over here. In fact, let's use same kind of indentation as I did do in Java, so it's consistent. And now I just provide the result. Okay, done. So again, this is just the same code, but written in C. For the other one, which is this function, well, the problem is I don't want, because this is recursive, and recursion is involving, if you will, because you're copying stack variables. What I'm going to do, I'm going to create a helper function. This is going to be a little static, which means internal, JLong, say fib, just fib, that takes a JLong of n, and simply goes and returns the Fibonacci like this and this. So this essentially is equivalent to what I have in Java. The only difference is that I'm now going to call into that function from here and say return fib of n. So essentially, the reason why I did it this way as opposed to making this into a recursive function is because I don't want to copy these two arguments every time I recurse into my own function. But I should now be essentially done. Appearing, of course, any sort of typos or mistakes. This is where we are now. We've written all of this. Okay. The next step, of course, is to build the makefile, and once we have the makefile, we can produce our final result. So let's get that done. Okay, so I'm gonna go back in here and create a new file. I'm gonna call it, it's just a file, I'm gonna call it android.mk. That's it, it's here. And what I'm gonna do is in this file, I'm going to create a number of entries. We'll actually talk more about this file. I just want to get it working first, and then we'll come back to what exactly, do all these things mean and what else can we do here. So first of all, I'm going to say local path is, and I'm going to call into simply a GNU macro called call my dir, which sets up the local path variable to the current directory. Then I'm going to say include, and I'm going to say clear vars. What that means is that it'll clear all of the variables that start with local except for the local path, if any exist. This will become more interesting later. Then I'm going to say local source files. I only really have one, and this one file is the Maracana Android Fibonacci native _fib lib. And .c, that's the source file. And finally, I have to define a local module. What is the name of the final shared library going to be? Well, I just for consistency reasons, I'm going to call it exactly this, of course, minus the extension. Now, this just defines the necessary arguments into the final part, and that is include build shared library. What that does is essentially executes, think of it as a function that says, what do I need to build and where do I need to store it? So it builds this code as a shared library by this name. You'll see the final name and what it actually is set to. Now what we're going to do is actually execute a build to test it out, and then we'll move on to a few more things to build, like, for example, the UI. So let's try it out. Ndk -build. If I hit enter, everything works correctly. It compiled by default an ARM-based shared library that I should now be able to load into my application and start using it.